Okay, good afternoon, and let's try this for part two. I just did this recording a minute ago on this recording, and it came back a chipmunk version, so I'm going to do it again. So just bear with me here. Very quick reminder what we did already last couple of days. We looked at a gas and how it behaves as far as pressure, temperature, and volume. We're assuming we have some quantity of gas, and it's an ideal gas, so it does what you expect it to do. I was showing you the other day that if we use the concept of physics of work is force times displacement. And that's great when we're talking about pushing a block across a table surface or something like that. It's a straightforward plug and chug. With gases, it's more convenient to look at pressure and volume. And I drive this out the other day. We can say the work done on or by a gas is based upon the pressure and the change of volume. And again, we can check the derivation if you want to look at that. So it turns out it's much more convenient to look at gases in terms of pressure and volume and how they're related, how the work done on or by a gas is related to those concepts. Very quickly, I remind you that just like in calculus class, when we look at the area in the curve tells us something, as does the slope. When we're looking at a constant pressure, if the pressure applied to a gas is constant and the gas changes its volume, then there was some work done either by the gas or on the gas, no matter what direction it's going. And that's calculatable because, again, the work is the area under the curve, so we can just look at the area of the curve and get that. And again, if the pressure is constant, and of course, in this case, the volume is changing, we can calculate the work as P delta V. It's a little bit more complicated when you have a constant temperature and the gas undergoes Boyle's law. It's not a straightforward calculation. Then we have to integrate from the 2 points, the initial, the final. But again, the concept's the same. The area under the curve is the work done on or by the gas, again, depending whether the gas expanded or whether the gas contracted, initial, final, or final, initial. So that's a quick reminder. And the other thing I just reminded you in class the other day was we always go all the way down to the axis. You'll see why that's important later. We're always going down to the x-axis. So the y is 0. Now, the other thing I reminded you about the other day was when looking at constant temperature, we have an isotherm, which we talked about yesterday. This is some temperature T1. If we have the same gas at a higher temperature, we still have Boyle's law. We're not going to violate that rule, but the T2 will be righter and upper, very inappropriate way of saying it. But as you work away further right and further up in the PV graph, the temperatures shift to the right as the temperature increases. So in this case, T2 is greater than T1. Of course, T3 is greater than T2 and T1. And that kind of makes sense. If you think about it, you need to memorize this, or you can just think about it for a given gas at a certain pressure and volume. As I change the temperature, it kind of makes sense that a gas at the same pressure will be at a higher, will occupy a higher volume at a higher temperature. So again, if that's common sense, great. If it isn't, then you can memorize it or come talk to me. But this is something you need to know in order to analyze gases and how they behave in this chapter. Now, yesterday we talked about isobaric. So if I have a PV graph, P and V, if it's isobaric, again, same pressure, then that's pretty simple. We have a gas, we're going to dump some heat into it, so we're going to add some Q to it. The gas is going to respond by either changing its temperature as Q is added, and then we have work on or by. So we're going to use the first law of thermodynamics to figure out what's going to happen here. In this case, if the gas were expanding, again, we'd have positive work being done on the gas. And we've got to sort of think our way through. Gee, I added heat, work was done on, so the temperature must have increased. The temperature must have changed. The lab activity we have designed for today is to get you to think about how these changes occur. And we'll show you that in just a second. The next one I like a lot, it talks about isovolumetric or isometric. Here we have the volume is fixed. The gas undergoes a change in pressure and a change in temperature, but there's no change in volume. Therefore, the area under the curve is 0. So it's kind of nice, the graphical interpretation is kind of nice to say. And finally, isothermal. Again, I'm just doing a speed review of this. Isothermal, ooh, come on back. Isothermal, the gas is going to undergo the typical Boyle's law. And again, we have the area under the curve. And we can take a look at whether heat was added, heat was removed, temperature increased, temperature decreased, nothing in this case, and then work done, positive or negative. And that tried to escape on me. So again, just a review of your notes from yesterday. Usually 2 or 3 times into this, it starts to sink in real nicely. Somebody asked me the other day if this is reversible. I think Ted raised his hand and said, can you reverse these processes? Absolutely. And I was just saying a minute ago, the gas can either do the work or the work can be done on the gas. Likewise, all these processes are reversible. You're going to see that in our lab activity today. Now, the lab I want to show you is it's one of these Walter Fent. You probably used a couple of these from Mr. Horgan's class. It's a little confusing. A few of the kids last year said that, hey, can't I do the entire homework without the lab? Absolutely. You don't need the lab to do the homework. If you understand the notes, it's easy. I like the lab because it shows you what we talked about in class in action, but it also shows you some other things. So if you want to do the lab sheet and answer the questions without this, that's fine, but I think there's some benefit to people to actually see this. The thing that's nice about this is they show you a gas, shown in green here, in a sealed container. There's a pressure gauge. There's a temperature gauge. We can show heat being added to the gas, like putting my blowtorch on it. And I can show the work. The pistons will be pushed out by the gas, or pistons be drawn in because something else external is doing the work. We have a familiar P versus V graph. This is the primary graph you want to look at, but I like this graph, this setup, because they also show you the volume as a function of temperature and pressure as a volume function of temperature. So you can see these other things. During this activity, you are going to select the process you want to pick. So if you want to look at isobaric, isochoric is isometric or isovolumetric. Slightly in the vocabulary, not AP. AP uses metric. And then isothermal. So you pick a process. You can look at, because this, for example, is isobaric, our pressure is going to be constant. So the pressure stays the same at 100 kilopascals. Then I can look at how the volume, and in this case, the volume goes from 1 to 2. You can see that here. And the temperature is somewhat fixed. If we start 300 degrees, the gas laws dictate that it has to go to 600, and this will make sense. Again, we can see it's on different isotherms, so this will make sense. If that's what you want to do, you can sort of lock that, run the initial straight, and then hit start, and you'll actually see the process. So you can see your graph doing what it's supposed to do. The thing I like about this, and I was kind of distracting you, I'm going to go back and do it again, the exact same process. Lock it in, hit the initial state, and again, the graph will do what you expect it to do, but now I can look at the picture and say, I add heat, I'm going to lock the pressure in, I'm going to look at, my pressure is not going to change, what's going to happen to my temperature and what's going to happen to my work being done by the gas. So I run it and I say, oh, looks like the temperature went up, I can see that, and it looks like the volume increased, therefore the work was done by the gas. So that's a quick simulation to show you how it works. Play around with the simulation, get the homework done. I know that you want to take pictures of you and your friends dressed up in lovely colors, and that's fine. But just get the lab done, see if it makes sense. When I get back on Thursday, we're going to do a bunch of AP release problems, and you'll actually see where you apply this. A lot of this lab is figuring out, was it positive work or is it negative work? Was it a temperature increase or a temperature decrease? So you're looking at the sign conventions, and then you're trying to derive some things out. So hopefully that makes sense. We'll talk about it when I get back. Thanks.